topic of this presentation is the fatigue analysis of a shaft with shoulder according to the FKM guideline. The example is taken directly from the FKM guideline from chapter 6, and I will start the fatigue analysis with the import of the input file. The calculation was performed with abaqus. So I will import an abaqus finite element model. The GUI asks the user whether it should plot also the higher order elements as linear elements within the GUI, which saves storage space and improves the performance of really large models. But in this case it's just a small model, so I say no, I want the full representation of the model. And after import we get this picture here, which is the shaft with the shoulder. I have calculated different load cases, which can be seen in this picture here. We can see the deflections for two different loading types. The one down here is a bending moment acting on the shaft with a nominal bending stress of approximately 150 MPa here in the thin shaft, and we have a torsional moment acting at the end of the shaft, which gives an equivalent stress of 170 MPa in this area, which actually is a shear stress of 100 megapascal. So this is the step torsion and the step bending. Just to give you an impression on what kind of loading conditions we are going to deal with. Going back to limit. The limit analysis is performed by moving from left to right, beginning with the definition of sets where we define which elements should be assessed. In the next step, we have to define the loads. After then, we have to define the FKM parameters, and the last step is to actually define the jobs, where the loading condition and setups are connected and the job is actually set up. Now, for the fatigue analysis of casted parts or machined parts which were modeled with solids, limit offers a default element set called SolSurf. This set will include all elements that have nodes that are positioned on the free surface. So what really happens is that the program will keep the outside shell of this model, the outer layer of elements, and will do a fatigue analysis with this outer layer, and all the elements within the volume are not processed in the fatigue analysis, since usually the cracks occur on the surface. So in this case we don't even have to define a set, because we have a default set we can use. So the next important thing to do is to define the loads. I will import two finite element results from the ODB. The first one is the torsion, which is the first step of the analysis. And The second step is the bending. So with create FA result bending. And step 2, I have defined that limit will import the stresses of the first and second step in the abaqus ODP. Now these results can be used to create complex loads within limit, and these loads are then used for the fatigue assessment. Naturally, it's possible to directly take these imported results for the fatigue analysis. So I will create loads from FA results directly, and now I have 2 loads that were directly taken from the FA result with the factor 1.0. But in the example of the FKM guidelines, actually we are dealing with oscillating loads. So the bending stresses in the nominal bending stresses have a minimum of 150 MPa and a maximum of 100 MPa. So actually I have to copy the bending and create a second bending load with a -1 as a factor. So here I have the bending acting from -150 to +150 MPa. And the torsion goes from -50 to +150 MPa. So I have to edit the first one, -50, which would be 0.5 as a load factor for the first torsion load. And when I copy this, torsion 2, and I will set this to +1.5, which will give us a torsion load or torsion stress in the part with the smaller diameter of the shaft of 150 megapascal shear stress. So with these 4 load cases, I have defined my loading situation, and with this means I can close this load manager. The next step is to define the setups. So I open the setup manager. I will create a setup called FKM base material. FKM base. I want to use base material module FKM, and I want to use a fatigue analysis, which is actually Dauerfestigkeit in German. And I select the sole serve. This is the default set in limit, which will take all elements at the surface of the structure. So the next step is to move through the FKM setup edit window and to define the necessary data. Here you can find stress concentration factors, which can be used to increase or decrease components of the stress tensor. Usually this is set to 1. With these factors you could, for example, simulate a drilled hole which is not included in the finite element model. So you could set these alpha values to 3, for example. Okay, but in our case we don't need that. We don't need a detailed output at this point. So what we have to do is we just have to go through different parameters. The first one is the material group. This is steel, and the yield stress, nominal yield stress is 800 megapascal, and the ultimate stress of the material is 1000. The effective diameter, according to this example, is 42 millimeters. Then we have some more data. Some more parameters for the material. Vergütungsstahl I will select, and we need section factor. Supporting effect is yes. Supporting effect means that if you have stress gradients normal to the surface, limit will calculate these and you will get a bonus factor which gives you higher stresses at the notch. Roughness is defined in micrometers. In this case we have I think 10 micrometers, correct. And we have overload condition 2. Overload condition 2 and a safety factor of 1.2. So those are the parameters which are used in the example of the FKM. Okay, apply. So the setup is done. What have we done in the setup? We have selected the code, we have defined the element set, and in the next step we have to define the job. So in the job, you first of all can select the number of CPUs you want to use with create job FKM base, for example, apply. Here I have to select my preference, which abaqus or which finite element interface I want to use. In this case it's the abaqus 612. I have to select a result file, in this case an ODB file. I have to select the setups I want to use in this run. We just have defined one. And I have to select the forces I want to use in this analysis. So everything is selected, and I can run the job by marking the line and pushing the run button. Here is the echo to one of the windows. Here already we have the analysis, and actually the run is finished already, and we're just writing data to the result files, which sometimes takes longer than the analysis itself. But the job is finished. You also get the status here in the job manager as completed. And if you want to post-process the results, you just push the view result button, mark it, push the view result button, and then the limit viewer pops up. And we can take a look at, for example, the maximum, let me see, FAT max degree of utilization for elements, for example. So what we see here is the result of the fatigue analysis. In this EL mode, which means one color per element, the complete element is colored in the color for the highest degree of utilization, and the correct way, but sometimes not as nice to post-process. The correct way is just to use the FAT max degree of utilization, and here you also see gradients of degree of utilization through the elements. And we have a degree of utilization of 1.1, and in the example of the FKM guidelines, the result is slightly above 1 with 1.02, and the reason for this difference is that the limit also takes into account not only the global bending direction in axial direction and the shear stress at the notch, but also due to the Poisson effect, we get some compressive or tensile stresses in circumferential direction, and this component is actually dropped or forgotten in the analytical approach, but in the finite element approach we also take that into account, and this leads to a slightly more conservative assessment. Now, in the beginning I said that if we use these default sets, we can actually just calculate the fatigue assessment for the elements on the surface. So if I hide half of the model and I rotate the model, then you can see that only for the outer layer of elements we have result data. Now, if you are interested in details of the FKM calculation, there are also text files available in the directory in which the fatigue assessment run was performed. In the .text file you get a detailed output of the analysis, and this way the analysis is not just a black box, but you can actually compare these values to hand calculations, and the complete flow also with temporary results is listed here in this text file, and you can use it for documentation purposes. Okay, so actually I'm finished with this short representation on the fatigue assessment of solid structures using FKM, and I want to thank you for your attention.